Hi everyone, this is part 2 of our lesson on solving trig equations. And basically what we did for part 1 is we took what I called simple trig equations, and what made them simple was that there was only one trig function in each equation. And we did that because I really wanted to focus on the concept of like how to answer a trig equation, meaning like do I just give answers off the unit circle, or do I use our plus 2k pi notation to represent all solutions, things like that. Well, today we're still going to remember everything from part 1, but we're going to look at some more difficult trig equations. And for the most part, what makes them more difficult is that there's going to be more than one trig function in each equation. So you might have an equation that has both a sine x in it and a tangent x in it. Or you might have exponents. You might have a sine x and a sine squared x in the same equation. And we want to talk about what to do with that. Basically, it puts a little extra work at the beginning of the question, the isolation step. Step 1 from part 1 was to isolate the trig equation. And that was real easy. It was like add this to both sides or divide both sides by this. And all of a sudden it said sine x equals some number. Well, that step is going to be a little tougher today. So back in 10.1, we talked about how you can factor trig expressions. And that's going to be a big part of this. So I want to remind you guys of something that you learned way back when. We already reviewed it once this year. The name for it is called the zero product property, and it's basically how you solve equations by factoring. It says if you have two numbers, call them a and b, and a times b equals 0, the only way that can work is if one of those numbers was 0. 0 is a special number, and that's why the zero product property exists. So what that really means for you, the thing you want to remember, if you're ever going to solve any equation by factoring, whether it's a trig equation today or any other math problem you ever do, you always got to make sure the equation is equal to 0 first, or that doesn't work. So let's start with an example. Let's read it and kind of break things down here. And before I start the question, let's talk about what we see. It says find all solutions for theta. That's basically another way of saying solve for theta. And then it has this right here. It says 0 is less than or equal to theta is less than 2 pi. So what that tells me is, number one, we're answering in radians because I said 2 pi and not 360. And number two, we're answering between 0 and 2 pi only, so that's the unit circle. So I'm going to say UC for unit circle. Unit circle answers only. We don't need the plus 2k pi on these. Now, before I move on, I want to do a little side note here. Some people might be wondering, why do we have a less than or equal to here, but just a less than right here? Well, the reason for that is because 0 and 2 pi are the same place on the unit circle. So if that does end up being the answer, you don't need to say it twice. You don't need to say the answer is both 0 and 2 pi. We usually want to do one or the other, and we usually want to do 0. And that's why we put the or equal to there. So what we're saying when we put the or equal to on the 0, but not on the 2 pi, all we're really saying is if that is the answer, that one point right at the beginning of the unit circle, if it is the answer, call it 0. Don't call it 2 pi. And also, another way for me to write that using interval notation is like this. So I said 0, 2 pi, that's my interval from 0 to 2 pi. I put a square bracket on the 0, that means including the 0, but then I put a parenthesis bracket on the 2 pi, that means not including the 2 pi. So that's another way I could have worded this question. I could have said find all solutions for theta on the interval 0 to 2 pi. All right, so that was a long little side note there. Let's get back to the actual question. So the next thing I notice is that we have 3 different trig functions, and that's what I said is going to be different for today. I have a cosine theta, I have a sine theta, and then I have another cosine theta. So let's think about factoring. Now, before I even think about factoring, the first thing I do is make sure that's a 0 right there. Now it is. If it wasn't, I would make it a 0. If that was like a 1, I would subtract 1 from both sides and make it a 0. But I see it's a 0, so I make my little mental check there. I say, okay, I'm good. Let's try to factor. Now, when it comes to factoring, remember from 10.1, we talked about two types. You always want to look for common terms first. That's the easier type of factoring, and it's the one you always want to try first. So when I look at this question, I see I have a cosine theta here and a cosine theta here. That's a common term. Let's factor it out. So I'm going to factor out cosine theta. And remember, factoring out common terms is basically the distributive property backwards. You're dividing to take something out instead of multiplying to put it back in. So cosine theta divided by cosine theta is 1. So my first term is just 1. Minus, and then if I divide that cosine theta out, it'll be 2 sine theta. So I have factored it. It's equal to 0. What I'm looking at is what we just reviewed, the zero product property. So remember, if I wanted to match this with the zero product property, I could say this right here is basically A. This right here is B. And you have A times B is 0. So that means one of those two things equals 0. So either cosine theta equals 0, that was A, or 1 minus 2 sine theta equals 0, that was B. And that's what you're trying to do when you factor. We're taking this one very complicated equation up here. We're splitting it up into two that look exactly like our questions from part 1. So now all of a sudden it's just solve for theta. But you have to do it twice, once for each. Now the first one is already ready to solve. We have cosine theta equals 0. Let me get my answers for theta. So I look back at my directions, I realize, okay, I'm doing radians, and I'm doing unit circle only. So I'm going to get two answers. There's two places where cosine equals 0. It's the very top and the very bottom of the unit circle. That would be pi over 2 and 3 pi over 2. So I got two answers so far, but I might get more answers from the second one. So let's go finish that one. This one I need to isolate that sine theta first. So I would start by adding 2 sine theta to both sides. Or you could subtract 1, it doesn't really matter. We just need to separate those two things. And then we'll divide by 2. So basically what we have is sine theta equals 1/2. And that's going to give us two more answers. The two places on the unit circle where sine equals positive 1/2. If I draw a little sketch here just to show you my line of thinking. The two places where sine equals positive 1/2, if sine is positive, it's up. 1/2 would be like the first step up on either side. So you're going to get two more answers here. You're going to get, that would be pi over 6 and 5 pi over 6. Now your actual answer to the question is all four of those together. So for my actual answer, I'm going to say theta equals, and you can write them in any order, pi over 2, 3 pi over 2, pi over 6, 5 pi over 6. That's my final answer to the question, is all four of those angles. So we factored to take our complicated expression, split it up into two easy ones. We solved the two easy ones, and any answers you get from both of those two easy ones are answers to the question. Okay, so the other thing we did in 10.1, and 10.1 you're probably noticing now was kind of a lead into this section. Everything we did in 10.1, simplifying expressions using our identities, that's something else you can use to solve trig equations. So just like we did in 10.1, you can use all those identities we learned, that's reciprocal identities, quotient identities, Pythagorean identities, anything like that. You can use those to simplify, cancel out terms, and make things, again, able to be solved. So let's do this example here. Now, first of all, before we even start the question, when I say just solve for x, period, what that means is I'm asking you to answer in radians and give all solutions, which means we're going to use that plus 2k pi or plus 2n pi. I told you it doesn't matter what letter you use. Plus 2k pi or plus 2n pi to give all solutions. Now, as for the question, I look at it and I say, okay, well, I have two different trig functions again. I have a tangent squared x on one side and a secant squared x on the other. So what I want to do is use some identities to simplify this. It's always better if you can get fewer trig. If you can take like two different trig functions and change them to the same, that's going to help you solve. So I'm looking for a relationship between tangent and secant. And I think, well, let's see. They're not reciprocals. They're not cofunctions. But then I see, oh yeah, these were squared. This is tangent squared x and secant squared x. So I go, maybe a Pythagorean can help me. Now, it's not our main Pythagorean, sine squared x plus cosine squared x equals 1. It's one of the other ones. Now, remember, I told you guys when we went over this in 10.1, I said, let's say you forgot them. Let's say you're looking at it, you're like, I know there's a Pythagorean, but I can't, is it tangent squared x plus 1 equals secant squared x, or was it secant squared x plus 1 equals, you're trying to remember. So I said, you can always just go off, find some scratch paper off the side, write out the main one, and then you can figure out the other one by dividing by either sine squared or cosine squared. This one would actually come from dividing by cosine squared x. So on the first part, sine over cosine is tangent, so that would be tangent squared x. The second part is just a 1 because it cancels. And the third one, 1 over cosine, is secant, so that would be a secant squared x. So even if I forgot that second Pythagorean identity, I can go off to the side, find a little piece of scratch paper. I found the little corner of my board here. Just do a quick simplifying, divide by cosine squared x and simplify, and you remember the other versions. So I think what I'm going to do is I'm going to do this substitution right here. If secant squared x equals tangent squared x plus 1, I'm going to put that right there. So let's do that. Let's leave this side of the equation. 2 tangent squared x minus 2. Let's change the secant squared x into tangent squared x plus 1. Now, it's actually more like part 1 again. There's really only one trig function in here. In fact, I could subtract tangent squared x from each side to cancel this one. This would give me 1 tangent squared x minus 2 equals 1. And now what I'm doing is I'm isolating. So I would add 2 to both sides. And you get tangent squared x equals 3. I'm going to take the square root to cancel out that squared. And what I get is tangent x equals, now we do get a plus or minus. That's the most common mistake I see on this type of question. When you take a square root, you get a plus or minus. So we're going to get 4 answers here, not 2. But we get plus or minus radical 3, or square root of 3. So we need to figure out where on the unit circle tangent equals either positive or negative radical 3. So I'm thinking to myself, remember I told you when we did this in chapter 9, I said the tangents are kind of the hardest ones because you have to work backwards and unsimplify and see where it came from. Now a radical 3 comes from having square root of 3 over 2 over 1/2. Because the 2's would cancel, you would get radical 3 over 1, which is radical 3. So if tangent is radical 3, that's because sine is radical 3 over 2, and cosine is 1/2. So on the unit circle, we squeeze it in here, squeeze it in a tiny one, that would be, one place would be right here. That's where sine is radical 3 over 2 and cosine is 1/2. So one of my answers is going to be, that would be pi over 3. Now remember, there's actually another one right here. But you don't need that one. I told you guys with tangent, you're getting 2 answers, but instead of using the plus 2k pi, you can just use the plus 1k pi, or basically plus k pi, and that'll take care of both of them. So you don't need to put 4 pi over 3 for this. What you do need is this answer right here. Because that's where sine is positive radical 3 over 2, cosine is negative 1/2, and that's where you get the negative version of your answer here. So for my other answer, what I would say is 2 pi over 3 plus k pi. And again, technically there's also an answer at 5 pi over 3. That's where sine is negative radical 3 over 2 and cosine is positive 1/2. But if you're using the plus k pi notation, you can just do the first one of each. So basically I did this one right here and this one right here. And I stuck a plus k pi on the end of them instead of having to write out 4 different answers. Instead of also writing, I could have written the answer I did the way I did, using plus 2k pi instead of plus 1k pi. But then I would need 2 more versions of that underneath. I would also have to have 4 pi over 3 plus 2k pi and 5 pi over 3 plus 2k pi. And that's still the correct answer, but it's unnecessary. It's extra writing, and it's unnecessary. All right, so that was a good question because we had to use Pythagorean identities, and also the inverse tangent part is, remember, and we mentioned this in chapter 9, inverse tangents are always a little bit harder than inverse sines or cosines because you have to do this part right here. You have to look at the number and not just see it on the unit circle. You have to see where it came from having done sine over cosine. All right, I have one last example for you guys. Find all solutions for theta. Theta is between 0 and 360. So this time, I'm asking you to answer in degrees and unit circle only. I said just between 0 and 360. Don't worry about the plus 360k or anything like that. I also did the same thing as before. I put the or equal to here and not here. That says if one of the answers is that exact point that is both 0 and 360, call it 0. Okay, so now let's look at the question. This has 2 different trig functions. One of them is a sine and one of them is a cosine. And one of them is squared. That's good. So remember, the relationship between sine and cosine from 10.1 is that as long as it's squared, like I'll focus on this one right here, you can always turn it into 1 minus the other one squared. So like this sine squared theta, I'm going to turn into 1 minus cosine squared theta. If it was a cosine squared theta, I would turn it into 1 minus sine squared theta. So let's do that for our first step. I'm going to leave this half, and I'm going to rewrite this sine squared theta as 1 minus cosine squared theta. So I got what I want at first. I got all cosine. That's good. If you can get it all to one trig function, that's probably best. But I have exponents. I have one of them is a cosine theta and one of them is a cosine squared theta. That probably means I'm going to need to do some factoring here. If I'm going to factor, I need it equal to 0. So let's get everything on the same side. Let's add cosine squared theta to both sides to cancel that negative 1 out. So I have a positive cosine squared theta. Let's put everything in order. I have a minus cosine theta, and then I'm going to put the minus 1 at the end. So I also kind of flipped those 2 terms on the left there just to get it in order. And don't forget, we still have this 1 right here, so it's still equal to 1. So now let's subtract 1 from both sides. And cancel that out, and now we got it equal to 0. So remember what we talked about back in 10.1. We have that perfect quadratic pattern, but instead of being a nice simple x, it's a cosine theta. But it's one thing squared, and then a term of that thing, and then a number term. So I could factor this one the same as I would factor x squared minus x minus 2 equals 0. And that would factor into x minus 2 times x plus 1. So my factors are going to be that exact same thing, but instead of having x squared and x, which go here and here for my x's, I have cosine squared theta and cosine theta. So when I factor it, It's not going to have x in front. It's going to have cosine theta in front. But the numbers are the same. One of them is a -2, and one of them is a +1. So just remember, if you have that perfect pattern, it looks exactly like the quadratic in green, but instead of having an x, it has a trig function. It doesn't matter which of the 6 trig functions it is, as long as it's the same for both. One of them is cosine theta, one of them is cosine squared theta. Or one of them is secant x, and the other one is secant squared x. Then that's fine, you can factor that. And now we're at the same place we were on basically our first example today. We have zero product property, a times b equals 0. So either the first one, cosine theta -2 equals 0, or the second one, cosine theta +1 equals 0. And I'm going to try to squeeze it in here. So for the first one, and now we're on part 1 again. These are simple, like 1 or 2 step isolate and solve questions. So the first one, I add 2 to both sides, and I get cosine theta equals 2. Now, automatically, right off the bat here, I say that's going to give me no solutions. So when you're doing, when you're solving trig equations, then basically this is a good thing to remember for sine and cosine. For sine and cosine, think about when we graphed it. The biggest it gets is 1, the smallest it gets is -1. So if you ever have sine or cosine equal to a number bigger than 1 or less than -1, just throw it out. No solutions. That can't happen. Cosine theta never equals 2. Biggest it gets is 1, smallest it gets is -1. Now the other one we will get some answers from. Let's subtract 1 from each side. Get me out of there and give you some room. We have cosine theta equals -1. That one we can answer. Cosine theta equals -1 right here. Here's my unit circle. Right there is where cosine equals -1. Remember, cosine is your horizontal component to the right or to the left. -1 means one full spot to the left. That would be, well, I was going to say pi, but then I look back at the directions. That would be 180 degrees, because I asked you to answer in degrees here. So I only get one answer to this question. After all that work, there was only one answer, and it's 180 degrees. And I answered in degrees. I answered unit circle only, which I wrote in red in the top corner just to remember, because that's basically our directions. All right, and that's it for today. So basically what you're looking at is some more difficult questions. Yesterday in part 1, basically the questions were just this right here. You know, how we're ending each question was part 1. Just simple 1 or 2 step and then inverse trig, answer the question. Today we're kind of combining this with 10.1. We're doing some factoring or simplifying work at the beginning, and then once you have that done, the goal is to separate it into easier equations that you can solve like we did in part 1.